to record to the cloud.
All right, let me see if I can mute everybody. I think I can mute all, and then I'm going to unmute Grace. I think, Grace, you'll have to unmute yourself now.
Got it.
Awesome, great. All right, so I think we have people still filtering in here, so we'll wait just a minute. In fact, I got to see what time it is. Okay, great. All right, so I guess without further ado, I'll introduce Grace and then let her get started with her presentation. Everybody, thank you so much for joining in our May AGU Geodesy Early Career webinar. We're so pleased to have Grace Neild, who is a postdoctoral research associate at the University of Durham, giving our talk today. Grace has we'll be talking today about solid earth deformation in the Antarctic Peninsula, and we will save for all questions till the end. So at the end, we'll have questions you can put in the chat or unmute yourself, but we will let, without further ado, Grace get started. So go ahead, Grace.
Okay, great. Thanks so much for the opportunity to present my work today. So good morning or good afternoon to you all, depending on where you are. So the work that I'm going to present today has been funded by the Australian Research Council, and it's work that I was doing with Matt King at the University of Tasmania. There's a few acknowledgements down the bottom here, but I'd just particularly like to mention Ashraf Kulali at the University of Newcastle, who has done all the GPS processing that you'll see in this presentation. There we go. Sorry, we just hit a small delay. So the Antarctic Peninsula is a really interesting region to study. It's quite tectonically complex. There's a subduction zone just on the west coast and a former subduction zone running down the west coast of the peninsula that shut down around 4 million years ago. It's also quite close to the plate boundary between the Scotia Plate and the Antarctic Plate. And there have been several large earthquakes that have occurred at this plate boundary in recent times. Now, we think because this region is quite tectonically active, that the underlying mantle viscosity is quite low. And what that means is that the Earth is going to respond relatively quickly to any forcings. So some of the sources of deformation that we see on the Antarctic Peninsula are long-term glacial isostatic adjustment. So that's the prolonged viscoelastic response of the solid Earth from deglaciation from the last glacial maximum around 21,000 years ago. So as the big ice sheet has melted, we see uplift in response to that. There's also been several ice shelves from around the peninsula that have disintegrated or collapsed in the past 50 years or so. And this leads to mass loss from the outlet glaciers. So the outlet glaciers that were flowing into those collapsed ice shelves lose their buttressing effect and they speed up and lose mass. And we've actually seen a viscoelastic response to these ice shelf collapse events, and that's been observed over decades, which reinforces our thinking that the mantle viscosity in this region is relatively low. We also think there's some volcanic activity going on, for example, at Seal Nunataks in the north of the peninsula, and post-seismic deformation following large earthquakes. And this is going to be the focus of my talk today. I'm looking at post-seismic deformation. So if you're not familiar with this process, earthquakes are caused by stress release. So as a fault plane moves past each other and releases that stress, we get an immediate co-seismic slip, as shown in the little schematic here. And these large stress changes propagate through the earth, and we also get a prolonged viscous response of the underlying mantle. And this usually happens at a fairly shallow depth compared to when we think of long-term glacial isostatic adjustment. So this phenomenon has been seen around the world. For example, in 1960, there was a large earthquake that occurred in Chile, magnitude 9.5. And deformation following this earthquake was observed 40 years after this event, and up to hundreds of kilometers away as well. So this gives you an idea of the scale of this kind of deformation. So in the Antarctic Peninsula, we have a relatively dense network of GPS that we use to observe deformation in this region. I say relatively dense, obviously it's nothing compared to the North America network or in fact Greenland, but we do pretty well in the peninsula. A lot of these stations are taken care of by the UK ANET project run by Pippa Whitehouse at Durham, and PolNet take care of a lot of GPS stations in Antarctica as well. We've also got several long-term continuous stations from around 1995. So this gives us a really good record of deformation over the past sort of 20, 25 years. So what can we do with these GPS? Well, there's lots of different things that we can measure, and lots of different ways we can use them. The sort of most traditional thing that we do with them is to constrain or measure long-term glacial isostatic adjustment. So this is what Pippa Whitehouse did with her W12A model. She took present-day GPS rates and used those to constrain her GIA model. The problem for the Antarctic Peninsula is that we don't know how much of this sort of long-term GIA signal is left, if any. If the underlying mantle is a low viscosity, it's quite possible that all of the response from deglaciation of the last glacial maximum has diminished by the time we get to sort of present day. So the second thing that we can do is to constrain Earth structure from recent or decadal ice mass change in response to ice shelf breakup. So here we can see the Palmer time series, and there's not much deformation going on at Palmer until we get to early 2002 when the Larsen B ice shelf broke up. And in response to that mass loss that was associated with that breakup, the Palmer station uplifted fairly significantly. The problem with trying to constrain an Earth structure from GPS is that we need to know what that longer term or background deformation rate is. And at Palmer, we've got a fairly good record of that. We can see a couple of years of observations before that breakup event. But for many of the stations around the peninsula, we just don't have that data. So we have to make some large assumptions about what was going on before. And the third thing that we can do is to constrain models of post-seismic deformation. Here we've got the GPS time series at O'Higgins, right at the tip of the peninsula, and we can quite clearly see a co-seismic offset at the time of a large earthquake and subsequent post-seismic deformation. The problem we have here is that post-seismic deformation is occurring on the same timescales as viscoelastic deformation in response to recent ice loss. They're both occurring on sort of decadal timescale. So it's quite tricky to think about how we can separate these signals out from the GPS time series. So post-seismic deformation in Antarctica, well, what's going on? It's actually not been studied very much at all. In fact, the only paper that's been published on this subject is from King and Santa Maria Gomez in 2016. And they observed in a GPS record from the East Coast that there was a change in deformation rate following a 1998 earthquake. And this earthquake was magnitude 8.2, so a really large earthquake that occurred just off the East Coast. And after they did some modelling, they showed that the whole Antarctic continent is potentially deforming fairly significantly in the couple of years following this large earthquake. So the work that I've been doing is to try and find out if the Antarctic Peninsula is affected by the 2003 and 2013 earthquakes that occurred at the boundary with the Scotia Plate. And if so, how much deformation do we see? So these two earthquakes occurred at the plate boundary here. The Antarctic Peninsula lies just down here at the bottom left. And the distance here is around 750 kilometres, so between the tip of the peninsula and these two earthquakes. They were both strike slip events and fairly large, so 7.6 and 7.7. So the question is, are these earthquakes large enough to cause post-seismic deformation on the peninsula? Is this something we should be worried about, or is the signal fairly minimal? So I've been making a model of these two earthquakes to try and find out. So the first thing, well, first of all, I'm starting with the 2013 earthquake, and that's because we have good GPS observations both before and after this event, so we can try and pinpoint the change in rate, in deformation rate. So the first thing I need to put into my model is fault slip properties, and I take these from this study by Yi et al. 2014. So I take the fault geometry and slip parameters in this published study and approximate them for my model. And the reason that I need to do this is because the model that I've made can only take one sort of geometrical plane. So I approximate the geometry and split that into 3 sections with a different slip and rake in each section. And I can then tune these parameters slightly to match the GPS observed co-seismic offsets. And this sort of accounts for these model simplifications and try and aim to make the model as accurate as possible. So once we have the fault geometry and co-seismic slip parameters, we can put these into a finite element model and predict our co-seismic displacement and post-seismic deformation. This finite element model has been built with the commercial software Abacus. It's a global spherical model, and it kind of consists of this low resolution mesh, and then we insert a really high resolution section where we have our earthquake and where we want to predict our deformation. We simulate the earthquake by making a fault plane within the mesh, and then we tell the model how much to slip at each of the nodes on the fault plane. So once the model has slipped, that's simulating our earthquake, then we run the model forward in time, and it's sort of allowed to relax viscoelastically, and this simulates our post-seismic deformation. I validated the model against the Arcada co-seismic analytical solution and the Visco 1D software from Palettes. The results of this benchmarking study have just been published in GMD. So we run the model and we get some model predictions, and then we can compare these predictions with our GPS time series. But first, I make an extra correction to the GPS time series to account for recent viscoelastic deformation due to ice change. So I'm going to try and explain this as clearly as I can. Like I said before, the viscoelastic deformation due to recent ice loss is occurring on the same timescales as the earthquake. So they're both occurring on the sort of decadal timescale. This is the uplift time series at Palmer. The Larsen B breakup happened in early 2002, and the large earthquake happened in late 2013. So when we want to find out the change in rates, or we want to isolate the post-seismic deformation, we remove the long-term trend from the time series, which then gives us our sort of estimated post-seismic deformation. But in doing this, we're essentially assuming that any deformation that was happening before was linear. In other words, all of the resulting change in rate is post-seismic. However, the study by Samrat et al. 2020 shows that deformation due to ice loss is non-linear. So there was actually a slowdown in ice loss from around 2011, which is then reflected in the deformation. So what we need to do is we need to take some model output and calculate the change in rate from this sort of the GIA model output, and then make an additional correction from the time series. So if you think about it this way, if we calculate the change in rate from GIA before and after the earthquake and it's 0, we don't have a problem. That's absolutely fine. But if there is a change in rate due to that ice mass loss, we need to correct that out of the GPS to try and isolate that post-seismic deformation signal. So if we remove the long-term trend at Palmer, we're left with subsidence here. And then we make this additional correction to account for that change in rate. I'll come back to this at the end if there are any questions about this. Okay, so we make this additional correction, and then what we can do is compare model output with GPS to try and refine our Earth properties. So I like to start simple. We tried lots of different 1D Earth models with a Maxwell rheology. So that's where we've got just one viscosity. The Earth has a fairly simple structure for these models. It's a 4-layer model, and we have an elastic lithosphere, a low viscosity asthenosphere, and then the upper mantle. And I try lots of different parameters varying these viscosities and the layer thicknesses as well. And we tried a total of 267 different Earth structures. I also tried a Berger's rheology, and this is sort of more commonly thought of as the most suitable rheology for post-seismic studies. And Berger's rheology is where we have two different viscosities. We have what we call transient viscosity, which is a low short-term viscosity, and then we have a steady state, which is sort of the longer-term viscosity. So when I try the Berger's rheology, I set the transient viscosity to be 1 order of magnitude less than the steady state. And I tried a total of 164 different Berger's models. So what does the modelled output look like? So we can have a look at the model output at each GPS station running from north to south in the east and the north and the vertical display the directions. It's quite clear to see that we get the most displacement in the east, and actually we get minimal displacements in the vertical direction, and that's because this earthquake is strike slip, so we only see vertical displacement at the most northerly station at O'Higgins. So for all the different models, we can calculate weighted root mean square error. And I do this using the north and the east direction only, and that's because, like I said, there's not much going on in the vertical, and the vertical time series is more prone to contamination from other signals. I use a subset of the GPS time series where we've got good observations both before and after the earthquake. So that gives us a reliable estimate of the post-seismic deformation signal. So this is a plot of viscosity with depth. So these are all the different earth structures that I've tested. The grey lines show everything, and the red line shows the best fitting models that are within our 95% confidence interval. So this is for the Maxwell, where we've just got one viscosity, and then we can do the same for Berger's, where we've got steady state given by the green line and the corresponding transient viscosity in blue. So the sort of best fitting models that we get seems to want a very thin lithosphere of 20 kilometers and an asthenosphere viscosity of 3 to 4 times 10 to the 18. And these two models are actually quite similar when we compare the steady state viscosity from the Berger's model with the Maxwell viscosity. So having a look at what that looks like with the best fit models compared to the GPS time series. Again, we've got east, north and vertical directions, and the Maxwell is in red with the Berger's in blue. And I know there's a lot going on this slide, but just to highlight that we do get quite a poor fit in the vertical direction. As said before, there's minimal post-seismic deformation going on here, and I think these sites are just affected by other sources of deformation or errors in that GIA correction that we've made. There's also some clear misfits at other sites. So for example, at Palmer in the east direction, we have quite a big misfit here. And again, that could be due to errors in that GIA correction that we've made. So we know that the Earth is not one-dimensional. So I tested a couple of different 3D Earth models to see if we could get a better fit to the data. So the first 3D model that I tried was to simulate the presence of a subducted slab under the peninsula. I said at the beginning that we've got an active subduction zone here at the South Shetland Trench, which would leave a sort of slab-like structure under the peninsula. So if we take a cross-section through this figure, this is what the model looks like. So we have an elastic lithosphere, and then we simulate this subducted slab with the high viscosity, and then include a low viscosity region above that slab. And again, varying the viscosity and thicknesses as well. The second 3D Earth model that I try is from a seismic model. This is from the ANT20 model from Andrew Lloyd. So the seismic data is used as input to the finite element model. You can see that in the figure, this is from Andrew Lloyd's paper in 2020. There's quite a lot of variation in viscosity around the peninsula, particularly between the east and the west coast. So these lateral variations in seismic velocity give us our lateral variations in viscosity. And where we have low seismic velocity in red, this approximately equates to low viscosity. And we combine this with a power law rheology, and that is a laboratory-derived flow law. So if you're interested in what that looks like, so when we use a Maxwell or a Berger's rheology model in the finite element model, we directly say this is the viscosity of this layer. But when we use a power law rheology, we do it slightly differently, and we calculate these diffusion and dislocation creep parameters and feed those into the model instead. These are calculated with this big equation, and you don't need to worry too much about it, but I just wanted to point out that it depends on a lot of things, including grain size of the mantle, water content, and then temperature. And the temperature is what we derive from the seismic velocity variations. And the viscosity in this kind of rheology is calculated afterwards. and it depends on stress from the model. So it's kind of a different way of thinking about how we assign viscosity in the model, and it actually depends on stress. So it can vary not only in space, but in time as well. Okay, so what do these model outputs look like? So this is the O'Higgins 3 time series in the east direction. Here's our best fitting Maxwell model. Here's our best fitting Berger's model in the blue. We get a slightly better fit from that Berger's model than we do the Maxwell. This is our simple 3D slab model. That's very similar to the Maxwell model, and we actually don't see an improvement in the fit. And then with the 3D power law, we actually see a worse fit again. So it's clear that with these initial tests, we're not getting a better fit. So I just want to talk about a couple of other things before moving on to the 2003 earthquake. So this Berger's model that you can see the output there in blue. This is our best fit model. And the Berger's model consists of a transient deformation and a sort of steady state deformation. And you can see this transient right at the beginning here with this kind of sloping line. This model has been run in 1 year time steps. And the reason that I ran it in 1 year time steps was to cut down on computation time, because I was running almost, 500 models. And had to cut down computation time somewhere. But what we think the transient response for a Berger's model is going to occur on a shorter timescale than that. So I reran this model with shorter time steps in the first couple of years. So we went down to 2.5 week time steps. And now we can see this really prominent transient response from the model in the first couple of months before it sort of tails off to the steady state deformation. So what's interesting is that when we recalculate this at a higher temporal resolution, we actually get a worse fit to the GPS. I don't have any answers to this. It's just super interesting to see. When we zoom in, we actually just don't see this transient response in the GPS time series at all. And that's why we get a worse fit. So it could be that the noise from the GPS is masking that, or the seasonal signals. But yeah, it's just really interesting that we're just not seeing that in the observations at all. So this time series was from O'Higgins, which is 784 kilometers from the earthquake. And further south, at about 1,000 kilometers from the earthquake, we actually don't really see that transient response from the model. I think it's just too far away to cause too much of that transient deformation in the first few months, which is interesting to note. So I'm also just going to come back to this correction that we made to the GPS for sort of short-term GIA. This is just a subset of our GPS time series, and the grey dots here are the original detrended time series. So here we're saying any change in rate after the earthquake, which is the dashed line here, is due to post-seismic deformation, and any change in rate from viscoelastic deformation to recent ice loss. So if we make that correction, you can see here in blue. What's interesting to note is that this correction is not the same everywhere in every direction. So for example, at O'Higgins in the east, there's barely any correction at all, but quite a large correction for the vertical and the north. we would expect quite a large correction in the vertical at most sites, because that's the predominant direction of motion from viscoelastic deformation to ice loss. There's also something going on in the east component around Duthiers Point and Palmer. This potentially could be some unexplained local signal. But yeah, that's quite a large correction that we potentially wouldn't expect. So we do know that this method is not perfect. So it's interesting just to compare our best fit models. We recalculate the best fit models using the uncorrected GPS as well. So we recalculate the WRMS error. So using the uncorrected GPS on the left and the corrected GPS on the right. This is the figure that we saw earlier in the presentation. And we can see that the range of best fitting models is much more tightly constrained when we correct GPS for ice mass change. However, the WRMS value is actually lower when we use the uncorrected GPS. The problem that we have when we're doing this is that the ice loss model output that I'm using for this correction, that has come from a study from Samrat et al. 2020. They're using GPS to constrain that model, and those GPS are uncorrected for post-seismic deformation, which we know is occurring on the same timescale. So we're already introducing a bias here. We're then using that model output to correct our GPS to then test a best fit as well. So this bias is propagating through. And I'd just like to highlight, really, I mean, there's no perfect answer, but it's just difficult to separate these two signals out from the GPS. And it's just really worth highlighting that. One possible solution is a sort of joint model whereby we implement both of these processes within the same modeling framework. Okay, so moving on to the 2003 Scotia Sea earthquake. There's not quite as much to say about this one because we don't have GPS observations both before and after this earthquake. So we can't go through this same process of trying to constrain an earth model. So what we do instead is to take slip properties approximated from the same Yi et al. Study, 2014. So we take the approximated fault plane geometry and divide that into 3 sections, which each has a slip and a rake. And then we forward model that with the best fitting Berger's earth model from the 2013 earthquake. So what that looks like in terms of horizontal velocities, these velocities have been estimated over the period 2004 to 2011. So this is the 7 years following that earthquake. And you can see a sort of northeast motion to these velocities. What's interesting to compare this to is that it has been reported that O'Higgins, which is this station just at the northern tip here, is moving 2.3 millimeters per year southeast. This has been reported by Argus et al. 2011 and 2014. And they report that this is the opposite direction than expected from ice loss, and that the cause of this is unknown. So we know that the cause of this is not the 2013 earthquake because the data they use predates that earthquake. However, we could attribute some of that to the 2003 earthquake, which is moving 0.3 millimeters per year in the east direction. So there could definitely be some contribution from this earthquake. if we just want to compare the magnitude of the velocities between the earthquakes, so the 2003 in blue and the 2013 in green, that's for the 7 years following that earthquake and the 6 years following that earthquake, we can see that you get a much bigger response from that 2013 earthquake. And that's because, first of all, it was bigger, but it is slightly closer to the peninsula as well. So where does this leave us? Well, the combined rates from these two earthquakes, they are affecting the Northern Peninsula. And if we add their velocities together and sort of have a look at what that looks like through time. So these are velocities computed every 5 years. So we can see that from 2015 onwards, we get a slight decrease in the velocities, and they're also changing direction as well. So 50 years after these events, we're still seeing quite a lot of post-seismic deformation, particularly in the east direction, and a little bit in the north as well. So just to sum up, the Antarctic Peninsula is undergoing post-seismic deformation. These earthquakes are large enough to cause that post-seismic deformation on the northern Antarctic Peninsula. And we see up to 1.5 millimeters per year velocity in the east direction. We've been able to compare model output with GPS observations to constrain an Earth model, and the preferred models would like a thin lithosphere and an asthenosphere of around 3 to 4 times 10 to the 18. No 1D Earth model fits all sites in all directions, but initial 3D models also don't improve the fit. The Burgers rheology is the preferred rheology. We get a slightly better misfit than with the Maxwell, but that transient response is potentially beyond detection of GPS, whether it's being hidden by seasonal signals or noise, not quite sure. And if we think about the sort of wider picture of this, post-seismic deformation is potentially affecting the whole Antarctic continent, and the geodetic measurements that we're using to constrain models of GIA. So by not accounting for this signal, we're introducing bias into those GIA models, and that's propagating through into when we're correcting GRACE data to estimate present day ice loss from Antarctica and hence sea level rise as well. GPS is a really useful tool, but it's complicated by the need to separate these signals, particularly post-seismic and ice mass change signals in the peninsula. They're occurring on the same timescales. So we need some way of correctly accounting for all the signals that are in the GPS so that we can accurately use them. Thank you for your attention.
Great, thanks so much, Grace. I am going to now unmute folks and let people chat. If they have questions, feel free to raise your hands if you have a question. I also see a few people coming in. Terry, do you have a question to start us off?
Yes, I do.
Thank you.
Hi, Grace. Thanks for the nice talk. I was wondering if you could just summarize for us how your results in terms of lithosphere thickness and asthenosphere viscosity compare with your previous modeling from GIA and also to the seismic data.
Yeah, so the sort of Maxwell or Burgers steady state asthenosphere viscosities that we're getting of around 3 to 4 times 10 to the 18 they're consistent with the previous work that I've done for the peninsula, although they're a bit higher than some subsequent work, which indicates around 9 times 10 to the 17. So there is a little bit of variation there. A lithosphere thickness of 20 kilometers is very low, very thin.
It is, yes.
You wouldn't see that from a GIA model. I think the best fit model for my previous work was about 130 kilometers. I think this is partly to do with the time scale of the stress change, because with post-seismic, it's an instantaneous stress change from the earthquake. You tend to see a thinner lithosphere because of that, I think. Yeah, it's not perfect, and I'm definitely not saying that this is the Earth model.
Yeah, okay. Thanks for the explanation. That makes sense.
Yes, we'll wait to see if anyone else has a question, but I have a question in the meantime, Grace, if you don't mind. I was curious about, you mentioned seasonal signals, but maybe I missed it. What did you do about seasonal signals, if anything?
Yeah, that's a great question. Personally, I didn't do anything about the seasonal signals. So Ashraf Kulali has done all the GPS processing for this work. So I don't know the full details of how he dealt with the seasonal signals. I can definitely find out and inform you if you're interested.
Great. Yeah. Well, sort of maybe a related question also was just I just am ignorant about what other data sets might exist, but I'm curious, are there any other long-term records of Antarctic Peninsula movements from tide gauges, or looking at coastline level changes or things like that? I mean, or is GNS really all we have?
Yeah, it's kind of it's not all we have. There are some tide gauges from around the peninsula, I think, but I think we're a lot more constrained with what we can do with them. I'm not a tide gauge expert myself. Any other observations tend to be the sort of longer term constraints, such as raised beaches and tilting lakes and that kind of thing. We're looking at hundreds to thousands of years. So when we're looking at processes on a decadal time scale, GPS is really the best data set that we've got to constrain our observations. Yeah. I know that people have looked at INSAR for the peninsula, but it's quite difficult to get reliable information out of INSAR for this region, but that is an area that people are looking at.
Great. And what about, are these earthquakes at all recorded on GNSS stations elsewhere in Tierra del Fuego or something like that, or are those too far away or not available?
Yeah, so there is one GPS station which is really, really close to the earthquakes, and that records it really, really well. The reason that I don't use that station to constrain my model is that this model has been built with the far field in mind. So specifically looking at distances of 300 kilometers or more from the earthquake, because we have to make a lot of simplifications to the model. If we predicted post-seismic displacement very close to the earthquake, it wouldn't be accurate enough. So that's the reason that we don't use that station that's really, really close. There are a couple of stations in South America, but they're further away than the ones on the peninsula.
Interesting. I guess, just sorry, hopefully if someone else has a question, they'll put it in the chat or raise their hand, but just super interesting. I guess my final question was sort of very interesting result about the Burgers time series change early on. So I was sort of wondering if the closer in stations do show that sort of a transient post-seismically, that gives a clue that it's really there and maybe hidden, or what do you think?
Yeah, I think it's something that I haven't looked at yet because these results only came in sort of last week and the week before. But it's something I want to look at to see how big that signal is close to the earthquake. Because you definitely do see the further south you go, the flatter it is. So yeah, potentially that station that's very close to the earthquake could pick up a really significant Virgus signal. Yeah, it'd be interesting to look at, even though we know our model isn't completely, really accurate very near to the earthquake.
Great. Anyone else have a question for Grace this morning or afternoon or evening, wherever you might be? I see we have people from all over the world on here. All right, well, not seeing any, I guess I will thank Grace again. Thank you, Grace. Really enjoyed your presentation. And if the recording has worked out, this will be available on YouTube, hopefully in a couple of days, if that's okay to post.
Yeah, thanks everyone for coming or tuning in afterwards.
Great, thanks again.